scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown.
That's the most dangerous. We call it Jupiter orbit insertion. J.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. It just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
Biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about a third of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we gotta go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion. J-O-I.
Nothing's really certain about what's going to happen.
Good evening, everyone. I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics at the University of Lincoln in United Kingdom. Very warm welcome to our already traditional Astro-Chat with Professor Don Kurtz. Hello, Don. Very happy to see you.
Glad to be here again.
Of course, we have those who come to Astro-Chat already several times before, but for those who are just maybe came for the first time, I say just a few words about Don. Don was born in San Diego and educated in the United States, and then spent long, over 45 years, distinguished career in astrophysics, which was split roughly half and half between South Africa and United Kingdom. Don has over 2,000 nights spent in telescopes, has over 500 of scientific publications, an author of a textbook, and prolific speaker all around the world over various topics in astrophysics. In his career, Don also served as Vice President of Royal Astronomical Society. And at the moment, Don is both visiting professor with us, School of Mathematics and Physics at the University of Lincoln, as well as extraordinary professor in Northwest University in South Africa, where Don now physically is. And thanks to internet, we can join together in this Astro-Chat. And now, floor to you, Don. Welcome to our next Astro-Chat.
Thank you very much, Andrei, and good evening, everyone. Let me now switch over to our presentation for the evening. And I trust that is up, Andrei. Andrei?
Yes, it's now there.
Right. Our chat this evening before we go to the question session is going to be about NASA's Juno mission. And you just saw a movie that NASA made 10 years ago when that mission was to be launched. It took 5 years to get to Jupiter. It's been there for 5 years, and it has just been given an extension until 2025. And so it's been doing great work and will continue to do more. And we're going to look at Jupiter through the eyes of Juno this evening. Jupiter's big, really big. And I say apologies to Douglas Adams. For those of you who don't know why, Douglas Adams wrote The Hitchhiker's Guide to the Galaxy. And in that book, he said, space is big, really big. And I've just downsized it to Jupiter. But Jupiter really is big. It's bigger than all the other planets put together. It's bigger than all the other planets, plus the comets and the asteroids and everything else in the solar system outside of the sun. Jupiter is 5 times farther away from the sun than our Earth is, and out there in the outer part of the solar system, it's much cooler. So when the planets formed 4.6 billion years ago, rocks crashed into each other, planets like the Earth grew, and out where Jupiter is, something like the Earth grew, and then it was able to hang on to the hydrogen and helium, which is what most of the universe is made out of. It's what the sun's made out of. And those gases piled on until Jupiter grew to be this giant, massive planet which dominates the solar system. There are other gas giants farther out than Jupiter. There's Saturn, Uranus, and Neptune. But Jupiter sits out there as a sentinel in the outer solar system. Now, we thought until 10 years ago that this was typical of solar systems, that big planets like Jupiter would form far from their stars where it was cool and they could hang on to their gas, and little rocky planets would be close to the star. But we found over 5,000 planets around other stars now, and there are lots of planets the size of Jupiter and bigger that orbit their stars in a matter of just a few days. We call them hot Jupiters. And at first we didn't understand that. Now with models of the way solar systems form, we know that many times giant planets like Jupiter migrate in the solar system through viscosity with a disk. They migrate in until they're very close to their stars, having formed farther out. Thankfully for us, that didn't happen in the solar system. If Jupiter were to migrate in, it would fling all the planets, including the Earth, out of the solar system. As it is, it sits out there in the outer part of the solar system. And as you saw in the movie, anything that comes near it, it can use as ammunition. But it has flung most of the comets and most of the big asteroids that would clobber the Earth out of the solar system, cleaned out the inner solar system, and made it relatively safe for us to live where we are. We don't get clobbered by extinction level events, usually more often than about once in 100 million years or so. It's been 65 million years since the last time. So that picture you're looking at in the background is a picture from Juno, and I love this picture. This is not science fiction, and this is not an artist's impression. This is a picture from the Juno mission of the atmosphere of Jupiter, high up in the atmosphere. That atmosphere is made of hydrogen and helium, methane, ammonia, and a few other gases. And what you are looking at are gigantic thunderstorms. These clouds right here are about 50 kilometers high. If you consider that our thunderstorms here on the Earth, maybe 10 kilometers up, usually less than that. These are gigantic by Earth standards, and look at the huge lightning storms here, these white spots here. Incredible storms. Jupiter's very, very stormy. In fact, what you can be sure is that if you're a weather forecaster for Jupiter and you want to predict tomorrow's weather, tomorrow will be stormy, and stormy beyond anything you've thought of for here on the Earth. I'll show you in just a little while. Why Juno for the name of the mission? Well, here's a painting from the 18th century by a Scottish artist of the Roman god Jupiter, who was the king of the gods and the king of the sky, and his wife Juno. And Juno was from quite an illustrious family. Her father was Saturn, and her son was Mars. And so this is really a very illustrious astronomical family, Jupiter and Juno, and that's why the mission has been named after her, the Juno mission. This is an artist's impression, taking a real picture of the actual satellite and placing it in front of Jupiter in the background. Now, we'll get in a few moments to how really big Jupiter is back there, but there's the satellite, and it's about 20 meters across this way and about 4.5 meters high. And without all of its fuel, its dry weight is about 1.6 tons. It was launched from Earth a little more than 10 years ago. Now, these dates are backwards. These are American dates, and they do everything backwards in America. So that's the 5th of August, 2011. It was launched from Earth. It traveled out in the solar system using its rockets to climb out beyond Mars's orbit, and then it fell back in the solar system with just the right timing to whiz by the Earth in 2013. And then in a gravitational interaction with the Earth gave it extra energy and flung it into the outer solar system, where eventually it got to Jupiter for the Jupiter orbital insertion 5 years after launch in 2016. Of course, to do that, it had to rob a little bit of energy from the Earth, and so microscopically, unmeasurably, that means the Earth moves slightly closer to the Sun because it lost a bit of its orbital energy to fling to fling Juno into the outer solar system to go meet Jupiter. I'm not going to go through all of the instruments on board, but this diagram's to show you that lots and lots of science is done with the Juno mission. It's studying, we will see, Aurora on Jupiter, incredible high energy radiation belts about Jupiter, way beyond anything the Earth has got. A magnetic field that is so big it stretches all the way to Saturn, another 5 times further than the Earth is from the Sun, out into the outer solar system. And of course, some cameras to take pictures, both in the infrared to look deep into the atmosphere to see how hot it is, and in visible light to show us the pictures we're going to see now. Let's look at the statistics. Jupiter's mass, 318 times the mass of the Earth. And as I said before, it's more massive than all the other planets added up. Its radius, 11 times the radius of the Earth. It would take more than 11 Earths to stretch across the diameter of Jupiter. It would take 1,300 Earths to fill the volume of Jupiter. And it's 5.2 times farther than the Earth is from the Sun. And we call that 5.2 astronomical units. Saturn's out at 10 astronomical units. At that distance, with the less gravity from the Sun, the gravity's weaker out there, it takes nearly 12 years for Jupiter to orbit the Sun. Now, I hope you've been seeing it in your evening skies. I know that occasionally it's clear in Lincoln. Remember, I lived in the UK for 20 years, and sometimes you can see the sky. Just before I started this talk, I walked out on my upstairs patio, which is just to my left where I'm sitting now, and stood out there and looked up at Jupiter and Saturn beautifully overhead for me. And earlier this evening, just after sunset, by the way, I walked out and looked at Mercury and Venus too. I've got a much better view of the planets down here in the southern hemisphere than you do, because their orbit sticks straight up in the sky for me, whereas at your far northerly latitude, kind of skims your southern horizon. But Jupiter's up now almost the entire night, and it's the biggest, brightest thing you can see off to the southeast if you go out in the evening. Even after this lecture, it'll be there waiting for you. Jupiter rotates very quickly. The Earth takes almost 24 hours to rotate on its axis. Oh, you're thinking, what does he mean almost? I do mean that. The Earth rotates in 23 hours, 56 minutes, 4.2 seconds. And in another lecture, sometime, we'll find out why that's not exactly 24 hours, which is what we use for our day. It has to do with the Earth orbiting the Sun. Jupiter, much faster. Even though it's so gigantic compared to the Earth, it rotates in under than 10 hours. But notice it rotates faster at the equator than up at the poles. There are huge winds blowing, and Jupiter has no solid surface. Its outer part is entirely gas. Deeper down, that gas turns to liquid, and deep inside, where the material is like the material that makes the Earth, the pressure and the temperature are so high, even though we call them rock and ice, they're more like a very hot fluid plastic. Jupiter's got an enormous number of recognized moons, 80, and as we see smaller and smaller things orbiting Jupiter, those numbers will go up. If you could go to the top of Jupiter in a spaceship, and you can't, you'll see that with the radiation, but if you could and hover in the atmosphere of Jupiter, you would weigh 2.5 times as much as you weigh here on the Earth. You would be extremely uncomfortable. If you'd like to know how uncomfortable, take whatever your weight is and pack up a backpack with 1.5 times that, put it on your back, and try to carry it. See how uncomfortable you are. I weigh 80 kilograms. If I were to put on a pack to make me have the weight on Jupiter, I'd have to put on a 120 kilogram pack. And that would really make it hard for me to move around. As I said, the atmosphere is mostly hydrogen and helium. Those are the things the sun's made out of, and the planets formed out of the material from the sun. There's some methane, ammonia, water vapor, some other trace gases. The radiation is phenomenal. As you saw in that movie at the beginning, the average radiation here on the Earth is about 1/3 of a rad. 300 rads would probably kill you, but I guarantee you 1,000 rads and you're dead. If you were in an environment, a nuclear accident in a nuclear plant, or let's hope it doesn't happen again, somebody sets off a nuclear bomb and you're close enough, 1,000 rads would kill you. The radiation near the surface of Jupiter is 20 million rads, and that will kill satellites too. That Juno mission is hardened. It's got lead and titanium protectors to shield it from all that radiation. But even so, as you saw in the movie, when the satellite came in close to Jupiter, it came in and it got back out again. And it spends most of its time quite a bit further away to stay out of this lethal radiation field. Magnetic field on Jupiter is 20 times stronger than Earth's is. And if that magnetic field, coupled with the little moon Io, and we're going to come back to Io, which is covered in live volcanoes, and Io spews out gases that get trapped in the magnetic field, and those get accelerated from pole to pole, and that's what produces this incredible radiation field. The lightning storms are in an environment where there's ammonia, and that ammonia actually makes the water, when it freezes, slightly mushy, and so hail forms in these big storms, but that hail is kind of mushy rather than hard like here on the Earth. And those big falling hail blobs are called mush balls. The core, as I said, is made out of what we quote say rock and ice, with about 10 times the mass of the Earth, but with a core pressure of 100 million atmospheres, 30 times the Earth's core pressure, and a temperature of 20,000 degrees. This material is not like rock and ice here on the Earth. So Jupiter is just phenomenal compared to all other planets. These are real pictures. This background picture here was taken by the Galileo satellite some years ago. This is the Great Red Spot right here. And that Great Red Spot is a hurricane, a cyclone, which has been observed in the atmosphere of Jupiter for over 300 years. Here on the Earth, when cyclones or hurricanes form, there's another big one out of the Atlantic right now. We don't know if it's going to hit the United States again. It's aimed that way. Those cyclones form over hot water, with the heat from the sun causing hot water to rise and form giant clouds up to 20 kilometers high that then have cold rain, and the rotation of the Earth causes the storm to begin to spin to form a hurricane with wind speeds up to 250 kilometers per hour. But when those storms go over the land, there's no longer any water for them to suck up, and the storm dies. Here on Jupiter, there is no land. And so this storm, which has wind speeds of 600 kilometers per hour, has been going for 300 years. Jupiter is covered in giant storms. The Earth down here is taken with an Earth orbiting satellite, but these two have been put in the picture to scale. This is how big the Earth is compared to Jupiter, and you'll see that the Earth is even smaller than the Great Red Spot, that gigantic hurricane that we know has been blowing for at least 300 years. There's a close-up picture of the Great Red Spot, and the winds in Jupiter's atmosphere, the winds blowing along the latitudes are typically about 400 kilometers per hour, and they're turbulent. And these pictures of Jupiter make great natural works of art. They make fantastic pictures and posters for your walls if you'd like them to get them for that. This is one of Jupiter's big satellites, Io. We're going to come back to that in a minute. It's about the size of the Earth's moon, and that's the shadow of Io being cast down onto the surface of Jupiter. I've put this one in just for its artistic beauty. Jupiter's now tipped from the position of the satellite. Its rotation axis is here, and these are the latitude belts and all the turbulence in the atmosphere. The colors are sort of true. They're true in hue, but they're oversaturated, so they look nicer to our eye. If you made them at the right saturation level, they would look much more pastel. But otherwise, the colors are not too bad. And this is a recent picture from Juno, and I'm just flabbergasted by this picture. Look at the storms. The Great Red Spot's up here, but look at all these other cyclones all over in the atmosphere of Jupiter. They are just everywhere. This place is phenomenally stormy. The weather's not understood, not by a long shot for Jupiter. Here we're looking at Jupiter's North Pole. This is with an infrared camera, hence it's been colored red, since infrared doesn't really have a color, but it's a long wavelength. And there's a giant hurricane blowing right at Jupiter's North Pole. And there are 1, 2, 3, 4, 5, 6, 7, 8 hurricanes dancing around it. And this entire set of hurricanes has lasted the whole 5 years that Juno has been orbiting Jupiter. We do not understand why that should be and how these things are forming and sustaining themselves. How big are they? These small ones are typically about 4,000 to 5,000 kilometers across. So this whole complex here is bigger than the Earth. At the other pole, at the South Pole, there's another hurricane blowing, but now it's only got 5 around it. And that's ongoing research in meteorology, the study of weather, but now not the study of weather on the Earth, the study of weather under phenomenally different conditions here on Jupiter. Understanding this may help us understand weather here on the Earth better too. This is a picture from Juno. We're going to have a little animation, first looking in visible light, and these colors are closer to true. And then in infrared light, we'll peel down and the infrared looks deeper into the atmosphere, where there are waves coming from the poles, and we can see the temperature. There are global winds blowing from the poles, as here on the Earth. And you'll notice the aurora up at the poles. Jupiter's got a permanent aurora. It's not one that just comes and goes like here on the Earth. The aurora is always there on Jupiter because of these phenomenally strong magnetic fields and because of all the material that's constantly blasted off the surface of the little moon Io. The Juno mission, after 5 years studying Jupiter, is now shifting its orbit. It's tipping the orbit up into a polar orbit that will pass over the poles of Jupiter better, get a better look at those polar vortexes, but also come in contact with these giant moons that orbit Jupiter. These are known as the Galilean satellites, after the Italian scientist Galileo, who first saw them when he turned a telescope on the sky for the first time in 1609. The closest one to Jupiter is Io. It's about the size of the Earth's moon. We thought it would be like the Earth's moon when we first went out there, but we discovered in its pictures it's covered in live volcanoes. They erupt largely sulfur, and so the moon's covered in what was molten sulfur that's frozen. The next moon out is Europa, a little bit smaller than the Earth's moon, and it's completely covered in ice. And you can see the cracks in the ice. And then the third moon out is Ganymede, and Ganymede is the biggest moon in the solar system. It's bigger than the planet Mercury. And you can see it has been bashed about over the lifetime of the solar system. And then the fourth moon out, which is about the size of the planet Mercury, is called Callisto, and it is completely covered in craters. It's the most cratered body in the solar system. Little Io here, the size of the Earth's moon, orbits Jupiter in 1.8 days. Only 1.8 days. It is so close in, it's really connected to Jupiter. Europa a little bit further out. Io is heated by the tides of Jupiter. You know, the tides here on the Earth cause the sea to go up and down. I live on the sea here in South Africa. My front garden has got a canal, a sea canal running in front of it where I can go kayaking. And I've got a tide table up and I watch the tides come in and go out every day from home. And I watch the changing of the tides with the changing of the moon and the change of the month. Here on Io, the tides from Jupiter are so strong that the friction has melted the entire planet, and that's why it's covered the entire moon. It's covered in volcanoes. A little further out, the tides from Jupiter are not as strong, but they're strong enough to crack all the ice in Europa. And these are the two I'm going to talk to you about now. Here's a close-up picture of Io. And just this is all molten sulfur that's been blasted out of volcanoes. Here's a volcano here called Pele, after the Hawaiian god of volcanoes. And there's where material's been blasted out of Pele. It erupts still now. Lots of erupting volcanoes on Io all the time. If you notice over here, there's a lake over here on the edge. It looks black, and that's a lake of molten sulfur. Now, molten sulfur is not black. Molten sulfur has the color of this frozen sulfur. It's orangish red. Why does the lake look black? Well, because the lake is flat, there's no wind, there's no atmosphere, and it reflects the sky. Here on the Earth, the reason lakes are blue is that a clear blue mountain lake is just reflecting the blue sky. It's not the color of the water. And here on Io, if you could stand on the edge of this lake, you'd see the stars reflected in the surface. It's reflecting the blackness of space. When the Voyager probes decades ago first flew by Io, they saw these volcanoes erupting live. And here's a picture of a volcano going off as the mission passed by Io and took some snapshots. Juno will be getting more pictures of this over the coming 4 years as it comes in for some close-ups of Io. And there you can see the volcanic material blasting out of the volcanoes on Io. Io spits out about a ton per second of material off of its surface all the time. That gets caught in Jupiter's magnetic field. It gets heated up. The sulfur gets split away, the oxygen gets split away, the electrons get torn off of the atoms, and those electrons get accelerated to high speed, and they bounce back and forth from North Pole to South Pole and produce those permanent aurorae, just as electrons here in the Earth's magnetic field bounce back and forth and produce the aurorae here on the Earth. And I think, Andrei, you're still sitting here. Someday for an Astro-Chat, I'll do a chat with you about aurorae here on the Earth and what causes them. So here's a NASA poster. This is a poster for an upcoming mission from NASA. We'll look at it in just a minute. But in our solar system, there's an ocean twice the size of all the Earth's oceans combined on this little moon, Europa, a little bit smaller than our moon. It's completely covered in water, which on top has got a crust of ice. Jupiter's heating from its tides keeps the water under the ice melted, and we wonder, could there be something living there on Europa? This is the closest place to the Earth where it looks like there might be chance of life like there is here on the Earth. And we want to find out about that. Juno's paving the way, and there are more missions coming. Here's an artist's impression of what Jupiter would look like from the icy surface of Europa. Here's a real movie made out of pictures of the surface of Europa. Many, many pictures, so you get all sides of it. And there's the ice, and it's all cracked by the tides cracking it. And when the ice cracks, it's probably about 4 kilometers thick. We're not sure. We will measure that with future missions. But when that ice cracks, that water from underneath wells up. And it contains material that looks like it might be the building blocks of life. Here's some real cracks. This is a picture of about 100 kilometers across on the surface of Europa. And here you can see where the ice is cracked, the water has come up, and it's stained orange with what are potentially organic molecules. Maybe something's living down there on Europa. Back to Earth. This is deep under the Earth's ocean, and this is something called a black smoker. We're 4 kilometers underneath the surface of the ocean. The pressure 4 kilometers down, just a moment, it's 1 atmosphere per 10 meters, 100, that's 400 atmospheres of pressure down here. And the water coming out of this volcanic vent is coming out at 300 degrees Celsius into 2 degree surrounding water. It's got dissolved minerals in it, and those condense into what are called black smokers. And here's a movie from a bathysphere, 4 kilometers down. And there you can see this dissolved minerals pouring out. There are bacteria that live on those minerals. And then you're looking now at tube worms. They're about 1 meter long. They live on the bacteria. They're crabs and fish that can live on the tube worms and other things that live there. There are entire ecosystems living around these hot water vents in the Earth's ocean. And they do not need sunlight to survive. No sunlight penetrates that deeply. This life survives off the internal heat of the Earth. We think it's possible that there might be such things on Europa. Underneath that ice, with the tides from Jupiter, there may be these hot water vents. And if life evolves easily, wherever the conditions are right, then there should be life on Europa too. Here's a still picture, much more closely in. Sea anemones, 4 kilometers down. These long tube worms, the reason they're so red is they're very, very rich in hemoglobin. It's the thing that makes our blood red, because the oxygen level is so low that deep in the ocean. They need a lot of hemoglobin to be able to process the oxygen. So we're hoping Europa's got life. There's another artist's impression of geysers blowing out of the surface of Europa. And here come the new missions. Here's the total poster I showed you earlier, just the top of it. This can be downloaded from the NASA Europa Clipper mission site. You can find the whole poster if you'd like to find it. It's due to be launched in October 2024. And it's going to fast track out to Jupiter. It'll take about 3 years to get there, and it will begin studying Europa in much more detail. We hope one day, with the success of these missions and better understanding of Europa, we will send another mission which will land on the surface of Europa. It will have a little reactor on it to make it hot, which will melt the ice, and it will fall down through the ice as it melts until it can pop out into the ocean, and then open up with a camera and go swimming and see if we can find some of these vents with life living there. That may happen in the next couple of decades. The European Space Agency has another mission to go called JUICE, the Jupiter Icy Moons Explorer. And the reason that Juno has been extended for another 4 years to 2025 is to study those icy moons in preparation for JUICE. JUICE will be launched in May 2022, 2 years before the Europa Clipper, but JUICE is just going on a normal low-energy orbit out to Jupiter. It'll take 7 years to get there. It'll arrive out there in 2029. So in this decade, we've got 2 major new missions going out to Jupiter. They will study Jupiter more. The planet itself remains of great interest, but especially these amazing moons that orbit Jupiter. Now, remarkably today, the composer Vangelis, if you don't know Vangelis well, most of you will know him from having composed the music of Chariots of Fire. And if you don't remember that, then those of you who are old enough to remember 2012, the opening of the London Olympics, when Mr. Bean played Chariots of Fire on his piano with his ridiculous skit. Vangelis is the composer, and he has composed music for the Juno mission to Jupiter. It's operatic, and you'll see that he's got a very famous soprano, Angela Gheorghiu, who's singing it, and that album has just been released today. I've not heard it. Let me leave that with you. Those of you who are classical music fans may want to actually buy this album and listen to the music. It's time now to go to questions. Thanks for your attention. Andrei, over to you.
Thank you very much, Don. Will appear on the screen, both of us. Yes, now we have time for questions. For those who are new to our Astro-Chats, please do type questions in the live chat below. And I actually see that questions are already arriving. And we have about 25 minutes for these questions. Let's start. I see there is a first question from Fernando Schlindwein, who is asking, is there a reason why we see many hot Jupiters as exoplanets, mostly due to the techniques used to find exoplanets? Or we think there are more of them than far Jupiters as ours?
Fernando, that's a very good question. Fernando, your question is, we have discovered lots of hot Jupiters and not so many out at the distance that Jupiter is from our sun. And you're right that that's a selection effect. The technique we're using to find the Jupiters is to watch the tiny dip in light when the planet passes across the star. And if the planet's orbiting the star in just a couple of days, then we get a dip every couple of days. And the missions we used, Kepler watched for 4 years. The TESS, the Transiting Exoplanet Survey Satellite orbiting now, looks at each batch of stars for 27 days. And if the planet passes every 4 days, we see dip, 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 dip. We pick it up. It's really easy. If we want to pick up a planet like Jupiter passing in front of a star, and it only does it once every 12 years, we've not even been looking for 12 years. And if we see a dip and we don't see it twice, we don't even know for sure it's a planet. There are other things that can cause the dips. So there's a big selection effect. We think there are probably lots more big Jupiters farther out. And as time goes by, those statistics will get better. Thank you for that very good question.
Okay, thank you. And then another question from Jim K. What has Juno data show us about the internal structure of Jupiter?
Oh, thank you, Gene. Have you been reading up on this? That's a pretty special question. We thought until recently that Jupiter had something with maybe 10 times the mass of the Earth, but kind of Earth density deep down inside Jupiter. And the Juno mission has got a gravity meter on it that can measure the gravity of Jupiter. Because it's spinning so fast, Jupiter is not spherical, it's flattened. And so the gravity differs as the Juno mission orbits it. And what it indicates is that Jupiter's core is kind of bloated. It may even extend halfway out to the surface of Jupiter. And I have to tell you now, we don't know why. That's a new finding from Juno. It's a great question. And that's a nice new scientific mystery to be solved.
Thank you, Don. And I'm just kind of going through questions. I see there is another question about this no solid surface on Jupiter from Lucky Boy. And how do we know that actually there is no anything solid there?
Right, Lucky Boy. Does your mother call you that? Maybe she does. Right. Jupiter is too big to have a solid surface. We know from its density that it's primarily made of hydrogen and helium. And hydrogen and helium don't go solid at the temperatures inside Jupiter. They have to remain gaseous until you get deep enough down inside where the pressure's high enough, and then they turn into liquid. But to have a solid, that solid has to be made out of elements that are heavier than hydrogen and helium. Now, sure enough, those are there. For example, silicon, oxygen, which if you put them together make silicon dioxide, which is quartz, and that makes up sand and most of the rocks on the surface of the Earth. That stuff's down inside Jupiter, but at 100 million atmospheres of pressure and at a temperature of 20,000 degrees, those things don't behave as rock. Even inside the Earth, where the core temperature is 6,000 degrees, the outer part of the Earth's core, which is iron, is not solid iron, it's molten iron. And then beyond that, the Earth's mantle, which is made of rock, is so hot it's plastic and it flows. It rises towards the surface and it falls back down again. And so that stuff down inside Jupiter that could make rock is not going to make a surface that you could think, oh, well, maybe if you could dive deep enough down, you might go walk on it. You're not going to do that at 100,000 atmospheres anyhow, and not at 20,000 degrees. You would simply become part of the plastic rock. Not a good place to go.
Thank you, Doc. There is a question from AC. Does Jupiter Aurora emit in infrared light?
Yes, Jupiter Aurorae do emit in infrared light. They emit in ultraviolet and they emit in the visible. You can see them through all the wavelengths that we've got cameras to look at them with. You can watch the Aurora on Jupiter with the Hubble Space Telescope. We watch those from here in Earth orbit. We don't actually need the missions out to Jupiter to see them. They emit in all those wavelengths. Those high energy particles, largely electrons, are slamming into the upper atmosphere of Jupiter, and they cause the gas to glow. And there's so much energy there that gas glows at all the wavelengths that we can see.
Thank you. And I'm just kind of putting some questions together. You mentioned about helium and hydrogen on Jupiter. There is a question from Jim Slide. As Jupiter is mainly hydrogen and helium, could it be considered as failed sun that could be a binary system?
That's a good question, Jim, and the answer is yes and no. Most stars in the sky are binary. For two stars to orbit each other is the norm. And so when you, especially the brighter and the hotter stars, when you go out and look at the bright hot stars in the sky, they're typically binary stars. That's usual. We found with our missions that are hunting for planets that almost all stars have got planets too. And so you can think of Jupiter as a failed star, but Jupiter has 1/1000th the mass of the sun. And the smallest stars that get hot enough that they can fuse hydrogen to helium, and that's the criterion that we use to define a star that can generate its own energy by the fusion of the lightest gas to the heaviest gas, they are about 80 times more massive than Jupiter. And so if you want to think of Jupiter as a failed star, it's a very failed star. It's not even close to the limit that would make it a star. Just below the things that are called stars, they're not quite big enough to be stars, but much bigger than Jupiter. We call them brown dwarfs.
Thank you, Don. A question from Jack Martin. Question is, how can such small body like Io spew out so much material and not run out? What is driving this mechanism?
Ah, okay. So what was the name of the person?
Jack Martin.
Jack. Okay, let me answer that, Jack, but I'm going to have to think on my, well, I was going to say think on my feet, but I'm sitting. Io is spewing out about 1 ton per second. And there are approximately 30 million seconds in a year. So that's 30 million tons of material. I'm afraid I have to go into scientific notation, Jack. So that is 3 times 10 to the 7th kilograms. The moon has got a mass a little more than 10 to the 22 kilograms, and so Io will be similar. And so Io spits out about 1 quintillionth of its mass every year. It would have to live for a quintillion years, 10 to the 15 years, or 1,000 times longer than the current life of the universe before it would blow all of that stuff off of its surface. So to us, it sounds like a lot, but it's not a lot compared to the mass of the planet.
Thank you. Thank you. Then a question about radiation on Jupiter from Simon Fry. Can you explain why radiation density is so high?
Yes, Simon, the answer is mostly because of Io. Io is orbiting Jupiter in only 1.8 days, and all that material coming off of its surface is immediately caught in a torus around Jupiter's equator, and that connects to the magnetic field, and the magnetic field is so strong that that material gets trapped in the magnetic field. There is a wind from the sun, as here on the Earth, and Jupiter is capturing particles coming out from the sun, but they don't dominate out at Jupiter. The material in the magnetic field is dominated by the emissions from Io.
Thank you. I see there is a still question about kind of solid matter inside of Jupiter from AC. Is the theory of Jupiter core composed of metallic hydrogen still a possibility?
AC, the idea that Jupiter has metallic hydrogen, and that metallic hydrogen will not just be in the core, that will come a long way out. Although with this bloated core now, maybe they begin to connect with each other. The standard theory of the inside of Jupiter has got the liquid hydrogen deep down as metallic, meaning it behaves as a metal and the electrons can move and currents can flow. And that is the source of the main theory for what generates the magnetic field. It's currents flowing in that ocean, if you like, of metallic hydrogen that generates the strong magnetic field.
Thank you. A question from Taj, who asked, is there a truth that Jupiter is shielding Earth from asteroids?
Taj, truth is a difficult term for a scientist. So we need to be careful with this word truth, but in the sense of scientific truth, our models are that Jupiter will have cleared out a lot of the debris from the inner solar system when it formed. So when people make models of how solar systems formed, and they're doing that, large numbers of theoreticians are doing that now, particularly to model the solar systems we're finding around other stars, they find in their models that when the big rocks collect and then gather hydrogen to become giant planets like Jupiter, their gravity is then so strong they begin to, by gravity, fling a lot of the rocks that are left over either into the star or out of the solar system, and they clear out a lot of the leftover rocks. And when you look at the history of our solar system, we can see on our moon that the moon suffered what we called early heavy bombardment. And the craters on the moon, they just came thick and fast for the first 500 million years of the solar system. And then for the last 4 billion years, the moon has not been clobbered so much. And so we can see that there was incredible bombardment for about 500 million years, and then it dropped off dramatically. And our best models suggest that Jupiter is the protector out there that flung a lot of that stuff away and left the inner solar system so that the Earth only gets clobbered every 100 million years for extinction events, and that's left enough time for us to get here. But it will come again. There are still asteroids that cross the Earth's orbit, and they will hit us, and that is an upcoming Astro-Chat, probably not for next month, but coming soon. We will talk about Earth impact and the things that hit. Now, since you've asked that, let me go back to my screen share. Bear with me here, Andrei and everyone. I want to bring back, you've asked the right question for me to share my screen again. Now, are you seeing Vangelis again, everybody? Andrei?
Yes.
Okay, I'm going to go on to the next slide. I put it in just for your question there. If I can get the next slide. All right, here's a picture from Jupiter from 2 weeks ago. This is taken through a very professional, but an amateur astronomer, taking it with his own private telescope. And that astronomer was observing through the Earth's atmosphere. I'm going to show you a movie, and you'll see that Jupiter wiggles around all over because of the blurring of the atmosphere. You can also see it's not so pretty, as you can see from the ground. There's the great red spot right there. And here's Io, and there's its shadow. And because Io goes around in 1.8 days, if you've got a little telescope and you can watch Io move across the surface of Jupiter. It's great fun. But just as Jupiter flings things out of the solar system, its strong gravity also attracts things to come crash into it. And when I do that talk on impact at some future time, I'll show you the pictures of the great impact on Jupiter back in 1994 when comet Shoemaker-Levy crashed into Jupiter. 2 weeks ago, a big rock crashed into Jupiter. It was several times bigger than the Chelyabinsk event in Russia in 2013, which blew out a lot of windows and blasted glass out and knocked people to the ground and caused quite a bit of damage. And this hit Jupiter just 2 weeks ago, and this particular amateur astronomer caught it happening. So let's watch over here where my cursor is. Right there. Jupiter, with its strong gravity, caused itself to get clobbered. So it may be protecting us, but it also collects a lot of stuff for itself. So good question, and thank you for that. It gave me an excuse to show that little movie. Let me now see if I can bring myself back again. Am I back, Andrei?
Yes, you're back. And actually, Taj replied that this actually the inspiration of my question. I saw the article and the video of the impact.
Okay,
So,
thanks, Taj. It gave me, I put it there just for you. I didn't know it was going to be you who would ask it, but I thought somebody might.
There is now a question from Alice Del Monte. Are the orbits of any of the moons decaying due to the immense gravitational pull?
Right. So who asked that question, Andrei?
Alice Del Monte.
Okay, Ellis, the orbits of any objects are stable forever in the absence of viscosity, for example. Well, let me take that back. There's gravitational radiation, which can cause orbits to decay, but that is insignificant for the moons orbiting something like Jupiter. And so for Io, Europa, Ganymede, and Callisto, they interact with each other. They tug on each other. There's some resonances between them, and that's what keeps the tides heating those planets. But they're not losing orbital energy by giving it up to, say, very small particles, which could carry away some of their orbital energy. Now, since you asked that question, you might be thinking of Saturn. Saturn's rings are millions upon millions of small moons, and those small moons do interact with each other, and the interaction flings some of them away from Saturn and causes others to fall into Saturn, and so the orbits do decay, and hundreds of millions of years in the future, Saturn's rings will disappear. But that's because of all of those moons interacting with each other. Io, Europa, Ganymede, and Callisto have got stable orbits, and gravitational radiation is too weak for a tiny thing like Jupiter to cause them to decay for that reason. That little bit of mass that Io's spitting out is not going to cause enough viscosity, and they will not decay in the lifetime of the solar system before the sun dies as a white dwarf and turns small and cold. And it will be white dwarfs we talk about in November when I come back from holiday and we have our next Astro-Chat.
Thank you, Don. There is a question from Dominic White. When will Juno reach the Galilean moons, and what sort of data will it get?
Right, Dominic, I partially can't answer your question because, well, you'll probably believe this. I'm not actually an expert on Juno. I work on stars. I just happen to love the planets too. I haven't looked to see what the exact schedule of interactions for the moons are. Juno has orbited Jupiter 35 times since it arrived in studying Jupiter. And given its extension up until 2025, it's going to orbit 42 times more. And those orbits will be designed so that they pass by those moons. It can't go orbit the moons. The moon's gravity is not strong enough for it to orbit the moon without Jupiter tugging it out of orbit. And so I don't know over the next 4 years which of those 42 orbits will pass around which moons. So I'm sorry, I can't answer that for you. Oh, and so you also asked what exactly it was going to do. And it's going to be using those instruments that it had on board, but it's primarily only going to be able to study the surface with the cameras, infrared camera and such. The magnetic fields of the moons are present but very weak, but the gravity meter may possibly tell us something about the interior, and I think that the intention is some of the observations will confirm how thick the ice is and how much of an ocean is present on the outer 3 moons.
Thank you, Don. I see another question from Lucky Boy. Why some planets form from gas like Jupiter and others from solids?
Right, Lucky Boy, that has to do with the distance from the sun. When the planets formed, and these are from our models of how planets form, at first dust, which is in the solar nebula out of which the sun formed, little bits of dust stick together, and we don't really understand how they stick. It doesn't work so well in the lab. If you try to make dust stick in the lab, it tends to break itself apart. But at some point, the dust sticks and make little rocks. The little rocks crash and grow into bigger rocks, like asteroids. You perhaps have seen pictures of them. And then those crash into each other and grow into even bigger rocks. And then the bigger rocks begin to collect the smaller asteroids until they grow into planets like Mercury, Venus, Earth, and Mars. We think something similar was happening out at Jupiter, but then Jupiter's 5 times farther from the sun. It's out beyond what we call the snow line, or even water's ice. And out there, those rocks were able to collect hydrogen and helium, which is most of what the gas of the sun is made out of, what the solar nebula was made out of. Here in the inner solar system, we can't do that. Here on the Earth, if you release hydrogen into the Earth's atmosphere, if you release helium, if you've had a party game where you've got a helium balloon and you've breathed it and then talked like Donald Duck, that helium is light and it rises to the top of the atmosphere. And at the top of the atmosphere, the temperature goes up to 1,000 degrees and the helium gets going so fast it escapes the Earth's gravity and it's gone. All the helium you ever breathed out when you were talking like Donald Duck has got lost to the Earth. It's not here anymore. So in the inner solar system, it's too hot here and the light gases escape the gravity. Out in the outer solar system where it's colder, the gravity could hang on to those gases because colder means they're not moving so fast. And the gases have got gravity too. And so as the planet grew with the gases, its gravity got stronger and then it could hold more and more and more gas. And the gas is most of what the universe is made out of, hydrogen and helium. And so they grew to these giant planets in the outer solar system. That also means we don't think those giant planets can form close to stars. And so all those stars where we've been finding hot Jupiters around other stars, those planets will have had to form in their outer solar systems and then migrated in. And that's given us some interesting new problems to try to discover the answers to.
Thank you, Don. I just there are more questions, but I want to ask one from me. Can you say, when actually approximately Jupiter been started to be called Jupiter?
Oh, maybe 3,500 years ago. You asked me approximately.
Okay.
And it was not too far from Odessa.
Thank you.
All right, let me give you the answer to that. The Babylonians lived in what is modern-day Iraq. Iraq has got a very illustrious history. And they asked the question, why do the planets move through the stars? Remember, they just looked up in the sky and there were little lights. They didn't know what they were. They didn't know the planets were planets as we did. They were just little lights in the sky. And they asked why they moved. And their answer was they were gods, and the gods do as they please. And their gods had names. And those names have come down to us. Now, we don't speak Babylonian, but their names were our equivalent to Mercury, Venus, Mars, Jupiter, Saturn, to Saturn. Those were the ones they could see. And Saturn was then the king of the gods, and then Jupiter. And I will give you a talk on the calendar sometime, and I'll show you how that is why the days of the week have got the names they've got. They're named after the planets, which were gods. And so in that sense, Andrei, Jupiter was not, Jupiter became Jupiter because of the Romans. Prior to that, it was Zeus with the Greeks. And prior to that, it was, I don't speak Babylonian, but was whatever it was in their language.
Thank you, Don. It's very, very interesting, in fact. And I see there is a generic question from Roger, who says, I'm truly entrailed by discoveries in cosmology, but how does one convince a skeptic that it has practical value for humankind?
You mean to study Jupiter or cosmology?
Generally, yeah, cosmology seems Roger is asking.
Do you know, there's a quote that I love, Roger, and it comes, just a moment. I would like to get this quote right, and I have it handy. Just bear with me. I know exactly where it is, and I will get it very, very quickly, namely because I just put it into a review paper for annual reviews of astronomy and astrophysics, which I was invited to write. And I absolutely love this quote, and I think it answers your question fairly well. So let me come down and just find the answer right here. The quote comes from Howard Florey. And if you do not know Howard Florey, he was an Australian who won the 1945 Nobel Prize in Medicine for bringing penicillin into medicinal use. And so I think you will agree with me. I know Alexander Fleming discovered penicillin, but Florey and his team turned it into a medicine. They have saved hundreds of millions of lives. And I think you and any skeptic would agree that that has great impact. But what did Florey say about his discovery? Florey said, people sometimes think that I and the others worked on penicillin because we were interested in suffering humanity. I don't think it ever crossed our minds about suffering humanity. This was an interesting scientific exercise. And because it was of some use in medicine, it's very gratifying, but this was not the reason we started working on it. I was telling that story to a group of farmers in Shropshire some years ago. It was a Shropshire Farmers Dining Club, very wealthy farmers. And one of them afterwards said to me, what good is astronomy? And when it said in that tone, he means, how can you make money out of it? And I explained to him that the best bet is just fund scientists and let them go out and discover whatever they want to discover. Most of it will just be interesting, but some of it will really pay off. But you never know ahead of time what's going to pay off. And he looked at me and said, I understand that. He says, my wife's got 25 racehorses. You never know which one's going to be a winner. Where I'm thinking to myself, how much does a racehorse cost? So the answer to your question is science pays off handsomely. I'll do another talk for you if you like soon, one I call The Stars Are Ours, which leads from the discovery of what powers the stars, hydrogen fusion, to our now efforts to build hydrogen fusion power plants, which are going to be the future source of energy for all of humanity. And that's the biggest payoff ever, because all money comes down to energy. Science pays off very handsomely. There are lots of other answers to that. But good luck talking to a skeptic.
Thank you very much, Don. And we basically 1 minute from the end, and there is just a comment from AC who says a very informative presentation, and on a personal note, saying hi from your hometown,
San Diego. Thank you, AC. I may actually visit next year if COVID will let me.
So we now arrive till the end of our time. We try to keep it 1 hour, so everyone can just spend 1 hour and enjoy. Apologies that we did not manage. I did not manage to read all the questions. Just time finished. However, thank you everyone for coming, participating, asking questions. Thank you, Don, again for this evening, and we hope to have more of these Astro-Chats, and we'll be very happy to see our wonderful public with questions, and you, Don, as well. Thank you all very much.
Okay, thanks for coming, everybody. Until next time.
Till next time. Bye.